Hello and welcome to the talk. My name is Holger and today I'm going to talk about continuous and monotone machines. This is joint work with Konecny and Florian Steinberg. Let me start with a short motivation and overview on what this talk is about. The main motivation of this talk comes from doing computer-verified proofs in a proof assistant in a context where real numbers and similar mathematical structures are involved. This is usually challenging as the set of real numbers is uncountable, and therefore we first need to define what we mean by computation on the real numbers. Our background is in an area called computable analysis. Computable analysis is a popular formal model for reliable computation on the reals and other uncountable sets that is realistic in the sense that it can in principle be implemented as software. Florian, one of our co-authors, is the main developer of a library for computable analysis in the proof assistant called Incone. However, in computable analysis, partial functions and proofs containing non-computational axioms arise naturally, making formal verification difficult. While this can be overcome in principle, for example, by making use of Cox-dependent type system, this usually makes proofs much more complicated. We therefore developed some techniques to formally specify algorithms in a way similar to how it is done in computable analysis. Our definitions turn out to be very useful for simplified verification, and we also show that our definitions are fully equivalent to those commonly used in computable analysis. In this work, we mostly focus on the theoretical aspects. However, it should be mentioned that we formalized the definitions in Coq as part of the Incone library, and that, for example, the above-mentioned equivalences correspond to a fully computational procedure to translate between these definitions. Before presenting our results, let me first briefly introduce some background from computable analysis and how this is formalized in Coq in the Incone library. The main idea in computable analysis is to encode objects of uncountable spaces by elements of the bare space, the space of natural number functions. We call such an encoding a representation. Formally, a representation for a space X is a partial surjective function delta X from the bare space to X. Elements of bare space that are mapped to some element X from X are called names for X. And we further call the pair of a space and its representation a represented space. Of course, the choice of the natural numbers here is kind of arbitrary, and we can replace it, for example, by finite strings or some other simple countable type, and often this can be more convenient when actually working with representations. In our Coq development, we therefore use a generalized notion of a represented space, where we replace the natural numbers here by some space Q, and here by some space A, where Q and A stands for questions and answers and can be any countable non-empty type in Coq. Let us consider an example how this definition is used. One of the most basic examples is to encode the real numbers by rational approximations. In this representation, both questions and answers are the rational numbers. Therefore, a name is a function from the rational numbers to the rational numbers that has to fulfill the specification that for any rational input epsilon, whenever we give it epsilon, it has to provide an epsilon approximation to X. That is an approximation to X with error at most epsilon. Next, we want to define notions of computability and continuity for functions on represented spaces. Let us first recall how these notions are usually defined on bare space. For this, we consider functions f from some space B to some other space B prime, where B is the space from some questions to some answers, and B prime is the space from some other questions to some other answers. So f gets some finite input Q prime and an infinite input phi, which is a function from questions to answers, and it can ask for the answers on some questions Q, and then it has to output the answer A prime, which is the value of f of phi of Q prime. So continuity means that for any phi in Q prime, F will only ask finitely many questions to this input, to the infinite input phi. Formally, this means that for any phi in Q prime, there's a finite list of questions of type Q, and when we replace phi by any other function psi that coincides with phi on this list, then the value of F will stay the same. Further, we say that F is computable if this box can actually be implemented by an Oracle Turing machine. That is, that there exists an Oracle Turing machine that when we input phi as an oracle and give Q as the input to the Oracle machine, then the output will be F of phi of Q prime. And as an Oracle machine can only ask finitely many questions to the Oracle in finite time, it should be clear that any computable function is also continuous. We can now define continuity and computability of function on represented spaces. For this, we introduced the concept of a realizer. A realizer for a partial function from a represented space X to a represented space Y is basically a function that acts on the underlying namespaces. That is, a function that maps names of elements X of X to names of F of X in Y. We can then say that F is continuous or computable if it has a realizer with this property. Note that the behavior of the realizer is only specified for names of elements of the domain of F. On other inputs, the realizer can be undefined or give arbitrary results. However, continuity is a quite strong requirement, and many functions important in practice are not continuous. In computable analysis, it is therefore common to also consider multivalued functions. A multivalued function, or multifunction for short, is technically just a relation, but the intuition behind it is different, and operations on multifunctions, such as composition, usually differ from those on relations. One should think of a multifunction as a function that can have multiple valid return values. The domain of a multifunction is all inputs for which the set of return values is non-empty. For example, the function in this picture has domain A, B, and D, and the value of B can be either 1 or 2. We can now easily extend the notions of continuity and computability to multifunctions by defining a realizer for a multifunction to be a function that, when given a name of an element of X, has to return a name of some element of F of X. One thing that should be mentioned is that we also allow the realizer itself to be a multifunction. So that just means that whenever phi is a name for some X in X, then it is in the domain of the realizer, and any value the realizer can take on such a name has to be a name for an element in F of X. We now come to the second part of the talk, where we'll show how we extend the concepts we have seen so far and how to implement them in a formal system such as a proof assist. Let us now again look at the picture of an Oracle machine that computes some partial function F. We can think of such a machine of working in a stepwise manner. So given some input Q prime, the machine performs some steps, of which some are querying the Oracle, and either after a finite time returns some A prime, which is the answer, or it goes on forever. So the Oracle machine computes a partial function, but we can actually capture what the Oracle machine does in a total function that we call M. Which still has the infinite input phi, and still has the discrete input Q prime, but now has an additional input, which is a natural number n. And the output is an option type. That means the output can either be of the form some A prime, which will be the answer, or it can say I don't have an answer yet and just output none. So formally, M is a total function that has as input an element from their space and pairs of natural numbers and questions from Q prime. And the output can either be an element of A prime or none. So it's an element of the disjoint union of A prime with a single new element. We then define a multifunction fm for such an m by saying that all possible values that m produces for some n are possible return values for fn. And finally, inspired by the Oracle machine picture, we say that such a function m is a machine for some multifunction f if fm is a realizer for f. Now we have already seen that an Oracle machine computing some function can be easily translated to this definition. On the other hand, if we are given a computable definition of a machine for some function f, we can define a computable realizer for this f just by doing an unbounded search for the first n such that the machine returns something. To visualize what we did with the introduction of machines, take a look at this diagram of a multifunction large f realizing a function small f. Basically what we did is we added another layer to this diagram for the machine m. And we can always get back from m to the realizer with the f assignment we have seen on the previous slide. The advantage of this approach is that m is a total single-valued function in contrast to the partial multifunction f. It is therefore often more convenient to operate on or to reason about m instead of f in a formal system. Let us consider a simple example on how to specify an algorithm with machines. The example we look at is the multiplicative inverse, which is a partial function on the reals. So the function f, partial function on the reals, which for x gives us 1 divided by x. And the representation we want to use is the rational representation of the real numbers that we have seen as an example before. Recall that the name for a real number in this representation is a rational number function that gives arbitrary exact rational approximations to that number. Let us first consider a realizer large f for this function. So a realizer for this function would be a function large f that when given and epsilon would give an epsilon approximation to 1 over x. Whenever epsilon is larger 0, and phi is an approximation function for x. So that means for all epsilon prime larger than 0, phi epsilon prime minus x is less than or equal epsilon prime. Now assume we already know that the absolute value of x is larger than some delta. Then we also know that phi of half of delta will at least be half of delta large. We can then choose epsilon prime as the minimum of delta epsilon squared delta divided by 2, and simply let f of phi of epsilon be 1 divided by phi of epsilon prime. This works because 1 over phi epsilon prime minus 1 over x is equal to this, which is less than or equal to epsilon. So the realizer would first have to do an unbounded search for an appropriate delta and then return this value here. Instead of such a realizer, we can also define a machine for this function, which has the same inputs as the realizer, but additionally has a natural number input. And we can use the natural number input here to guarantee that we have already found such a delta. So we can return the same as the realizer, where the parameter n can give us an appropriate delta. Or we return none if it doesn't. Now proving the correctness of m consists of 2 simple steps. The first one being that whenever phi is a name for some real number that is non-zero, there will be some n such that we are in the first case of this case distinction. And if we are in the first case of this case distinction, the value will be correct. So it will be an epsilon approximation for 1 over x. In computable analysis, there's a standard construction to encode continuous functions between represented spaces called the function space representation. In this part, we will compare the information we get from this function space representation to that of our machine definition. Let me first tell you how the function space representation is formalized in the Incone library. For represented spaces x and y, the function space construction automatically gives a representation for the space of functions between x and y that have a continuous realizer. The idea behind the construction is to encode the realizer itself as an element of bare space. The difficulty here is that the realizer has an infinite functional input, but elements of bare space only have finite inputs. However, we only want to encode continuous realizers and recall that for continuous functions, the value only depends on a finite subset of the infinite functional input. The idea now is that we encode the realizer as a function psi, where the infinite input is replaced by a finite function, and either this finite function is enough for the realizer to provide the answer, or the realizer gets stuck because it needs answers to some questions that are not in the domain of the finite function. So the type of psi should be as follows. As questions, we give psi a finite function that we can encode as a list of question-answer pairs and a discrete question q prime for the output. So a pair of a finite function from q to a and a question from q prime. And if the finite function is already large enough, psi can just return the answer from a prime. Otherwise, it returns a list of questions that the realizer would ask to the infinite input and that are not yet contained in the finite function. So what it returns is either an answer from a prime or a list of questions from q. To make this formal, Incone defines a so-called universal that runs names of this form. The universal has two infinite inputs, phi and psi, and a discrete input q prime. And the idea is that if psi encodes a function f, then the universal returns f of phi of q prime. So what the universal does on input q prime is first it gives the empty list and q prime to psi. Now psi can either return an answer or ask a list of questions. So let's say it asks a list of questions. Then this universal will just forward this list to the other infinite input phi, and then append the return values to the list that is given to psi. And this procedure will be repeated until eventually psi will return an answer. So if it returns an answer, then we will just forward the answer to the output. We then call psi an associate for a function on bare space. If we fix psi as the infinite input here to the oracle, then we get a realizer for f. And we can define the function space representation by saying that psi is the name for a function if it is an associate of a realizer of this function. It can be shown that any continuous function has a name in the function space representation. Now, associates can be quite complicated, and a machine basically contains the same information about a function while being much simpler to handle. To make this formal, we want to give a procedure that automatically translates from a machine to an associate. Assume we are given a machine M and we want to get an associate from this machine. That is, given a finite function phi and a question q prime, we have to return either the answer or a list of questions such that the machine and the associate implement the same function. The first problem we have is that the inputs of the machine and the associate are different. The machine gets a total function as an input here, and a pair of a natural number and a question as an input here. Of course, what we can do is we can extend phi to a total function by returning some default element for inputs outside of the domain of phi, and then give q prime and this extended function to m. And for the integer input, we just start with 0 and then just increase it until we find some value. However, there are some problems with this approach. First, M might never return a result, and even if it does, as we cannot see which values of the input function M asked for, the result of M might depend on some of the default values in the extension and might therefore be wrong. What we do know is that if M is continuous, then if the finite function is large enough, this will not happen. However, we need to make this continuity information explicit. So what we do is we assume we are given a second function mu, which is a modulus function for M. So a modulus function means mu has the same inputs I, q prime, and a function phi as M. But instead of the return value of M, it returns a list of questions, which gives the elements of the functional input on which the value of M on those inputs depends on. So given both M and the modulus function mu, what we will do is we first start with the modulus function. So we start with 0 and q prime and give it to the modulus function. And then the modulus function will return a list of some elements. We then check if this list is already contained in the domain of the finite function phi. If the list contains any elements that are not in the domain of the finite function, we return the list of these elements. Otherwise, we know that M on these inputs will only depend on values of the input function that are already contained in the finite function. So we can just give those inputs to M. Next, we check the return value of M. If M returns an answer, that is, if the result is not none, we know that this will be the correct answer and can just return it. Otherwise, we want to increase the effort parameter I. However, as this could go on forever, we have to return something eventually, even if none is returned. So what we do is we only increase I if it is smaller than the length of the finite input function. Otherwise, we break out of this procedure and just return a list with some arbitrary default question. If I is smaller than the length of the finite function, then we just increase I and repeat this procedure. If we give the function constructed in this way to the universal we have seen on the previous slide, it will give the same function as the machine. So we have an associate for this function. Now there's one more technical detail we need for this to work. Namely, the value of mu should also only depend on the finite function. So mu has to be its own modulus function. We call such a modulus self-modulating, and it can be shown that a self-modulating modulus always exists. Summarizing the construction on the previous slide, we define a continuous machine as a pair of a machine and a self-modulating modulus. It should be mentioned that requiring the modulus function to be self-modulating is usually not a very strong assumption, as most modulus functions that one would write down naturally turn out to be self-modulating. On the previous slide, we have shown that there is a fully computational procedure to translate from continuous machines to associates. And actually the same holds for the other direction. So there is a fully computational procedure to translate from associates to continuous machines, but I will skip the proof here for time reasons. There is one more aspect that I want to briefly focus on. Often defining operations on continuous machines can be greatly simplified when a certain property that we call monotonicity holds. Monotonicity basically means that as soon as the machine returns something, it sticks to this value and never returns anything else. So that means that if there is some n such that m phi n of q prime returns some a prime, then the machine will still return the same if we increase n. Similar to the case of continuous machines, there's a technical detail for the modulus that is important when working with machines that are monotone. Namely, whenever m returns something for some n, then the length of the list returned by the modulus on the same inputs will not increase when n is increased. We call the pair of a machine that is monotone and the modulus with this property a monotone machine. Now it is always possible to computationally transform a continuous machine into a monotone machine realizing the same function. But monotone machines often allow simpler definition of operations. For example, there's a quite simple algorithm for the composition of monotone machines. Okay, this is the end of the talk. To briefly summarize what we did, we introduced machines as a technique to specify algorithms inspired by the Oracle Turing machine model from computable analysis. By adding some explicit continuity information, we can use machines as names for functions. We can also automatically translate between our model and the more common way of encoding functions as elements of bare space. We implemented this procedure in Coq and formally proved its correctness. Some possible applications of these methods include, for example, verified exact real computation in Coq. Thank you very much for listening.